My name is Amir. I'm here to talk about how we got Python. We added Python to our org. Basically, from zero, we got it today, where it's most of the data scientists, this is the preferred language and tool. So I will share with you how we done it. A little bit of context, I work for Agoda. We do hotel, we're a travel agency here in Bangkok. I moved here 3 years ago, and part of what I do is in charge of the team that is using data science to improve all of these things. But also I'm helping in making it easier to do data science in a team that's called, we call it data science efficiency, where basically our KPI is to reduce the time to market of data science solutions. So when we set up to build our platform or to build more tools, we need to think about our users. Should I use it? Yeah. Cool. Hello. Is it better? Yes. So when we set out to build our tools and to build the research platform that we have, we need to first think about what we talk about when we talk about the data scientist and how to get data scientists to be impactful inside our organization. So the way we look at it is that a data scientist has two profiles, and he's moving back and forth between the two types of tasks, two types of things he needs to achieve, he or she. So on the researcher side, it's more stuff like reproducibility and insight and having a fast access to the data and a way to analyze and visualize it. But when you are wearing your engineer hat, you have a different set of concerns where you are more concerned about testing, traceability, and other stuff. Now, in most organizations, there's like this blue line that separates between the two, but what we are trying to do is make this line go away and make the same person be able to own his solution from the analysis and research side all the way to production where it brings value. So why is it hard? So this is an example of all the systems that a data scientist will have to interact with in order to be impactful. If I want to be end-to-end, to build something, do my analysis, and then put it in production, and I don't want to talk to anyone because maybe I'm not so friendly, then I will have to know how to use all of these systems. Now, some of them are research, some of them are more like operations, but the thing is that what we see is that users need to know how to sail from the first steps of data analysis or visualization all the way to scheduling and getting resources for your job to run in a scheduled production manner. So what we did in the last couple of years is try to unify all of these systems and make like a streamlined approach and make our tools, building tools that make it easy to use any of those systems. So a little bit of history, how we got to a point where we didn't have Python, because we really love Spark. And just maybe a show of hands, how many people here use Spark? Okay. 3, the people in the second floor don't use Spark, so. Okay, so Spark is a very cool framework. We use it for all of our data needs. It really helps us scale. Internally at Agoda, what we have is we run our own Hadoop and our own clusters. We don't use cloud, and we have big clusters. Our users have access to a cluster with 200 nodes, 110 terabytes of memory. And we started using Spark 5 years ago. It was version 0.6. Just for reference, today it's already 2.4 and 3 is coming up. We invested a lot into it. We developed in-house tools. We developed pipeline stages for machine learning. And we even have some of our own models built on top the Spark MLlib. And all of this was done in Scala. With Scala Shop, we are still, most of our code base is Scala. And it got us to a point where we have a lot of production Spark applications, and a lot of them even running concurrently. So we made Scala very easy. Writing Spark Scala application is very easy today. You can easily submit them. And that was cool and nice, but now why we needed more than that? So first of all, what we noticed at first that we need a repo, okay? The read, evaluate, print loop. Iteration using submission leads to a very slow dev cycles, okay? If you have to submit your app, wait for it to finish, even though if you have your Spark application, you have the nice UI, but still, you cannot really control. You cannot play with the data. You cannot see what you're doing. And it makes it very hard to debug, and you don't even really know what exactly is going on. So in order to tackle this, the first thing we went to is the Jupyter and the great Jupyter notebook system. So the notebook approach, I'm going to show a small GIF here, not so high quality, but bear with me. And so we have an internal system called Zoidberg. The name comes from the fact that we allow engineers to choose the names of systems, and that's usually a bad thing. And what we can see that we made it work that user can submit the Spark application from his laptop, and then basically the code will be packed into a jar, put into HDFS, and then the user can access it from a Jupyter notebook. So even if I started my day writing a Scala class, by the end of the day, I can make it run inside the notebook and then add all the visualizations and all the cool stuff that the notebook has to offer, even though I'm running a Spark application in Scala. So this was a way for us to connect what we already had in Spark and Scala, all the utilities, all the connection to the various data sources, but still also get all the great things that's come with the Jupyter notebook system. So that was the first step, but then slowly we saw that there was more and more Python to offer that might help us in our stack or might help us with the tasks we have in hand. So we got today to a point where we are getting basically the both of both worlds, right? So some things that you can find only in Python and they are uncomparable, like PyTorch, TensorFlow, Pandas, and NumPy. These are great tools that, unfortunately, for Scala, we couldn't find an equivalent. And not to mention visualization, which basically doesn't exist in Scala, and Matplotlib and Plotly make it very easy to use in Python. But still, Scala has, of course, its own merits, like threading, types, and a lot of also cool packages like Breeze for some NLP. The main thing that we got from like being able to control the environment and build our own tools on top of it is that we were closer to our users, so we know exactly what was their pain point and what was important to them. So when we developed our REPL, some of our fast wins was develop our own Jupyter magics. So basically, we have a magic that we have like a great library developed by one of our data scientists that takes a data frame and calculates its statistics, goes column per column, and gets you the histogram, the top K, does a lot of statistical analysis on the data frame. But that was done in Scala. And in Scala, as I said, we don't have much ways to visualize. So by using Jupyter and leveraging the magic system that it has, we were able to give our users a way that a one-liner, he can just create his data frames in one system, move it to Python for visualization, and keep on working inside Python. So these were cool things. And just to share a little bit how we got it to work. So it's based on two great open source projects called Spark, Magic, and Levy. So we have our big clusters with all of the machines. A user just submits code from his browser. Locally, there is a kernel which is doing the local computation. And then the code is sent via REST to the Levy, which is the session manager. Having a session manager is something that also allows you to start your work with one laptop, then close it, and then maybe continue when you're at home. So after the session manager gets your code, he passes it on to a dedicated Spark driver, and that Spark driver can have as much as 300 workers where the Spark code can know how to distribute. Then once the computation is done, the code is being returned to the user, and this loop happens very fast, and basically from your browser you get the power of 300, 400 machines in an easy way with all of the goodies and all of the utilities that we already have. So one thing we found out that's helpful, that user asked us for a longer timeout of the session. So basically, this is the main tool of research now. You make a research in the morning, you run some query, you calculate your data, you load it up to the memory of your executors in the cluster, but you still maybe want to go back to it tomorrow and not go through all the calculation. So because Spark has a feature that's called dynamic allocation, it can manage the resource in a smart way and only keep the executors alive that are needed to really hold your data in memory. So basically, once you load, we really save a lot of warm-up time for the data scientist. So once I build up my data frame, it can stay with me during the whole week, and I can keep on working with it without having to recalculating. And when I mean stay with me, I mean stay in memory. So that's a strong thing to have. And after we got the whole Spark and notebook thing figured out, some people said, okay, this Python thing, it's pretty cool. Do we really need Spark for everything? Maybe we can do some of the stuff just Python, or of course we also had PySpark, but when I say Spark, I mean strict Scala code. So some people said, hey, Python is enough for me. Just get me a way to connect to data. I already have, I can do whatever I want with Python. I don't need these to use Scala at all. So then Python has its issue, for example, dependencies and getting a correct environment to work. So what we decided to do is we allow our users to have access and control over the research environment itself. So basically, we have a system where we have a Git repository containing the Docker files on the dependencies needed that back up the notebooks or the script that the users are running. And then some of the data scientists just submit a pull request with changes to the environment, and they get reviewed by peers. And once the PR is merged, we automatically build it with our CI engine, which is TeamCity in this case. And then we publish the Docker image, and it's made immediately available for research. So having the community of people, also what it helps is like when one guy finds a good dependency or a good library, it's immediately available to all the other teams and all the other people. And it's a cool way to share some insights and how to use stuff. So that worked well for us. But still, the notebook is not 100% perfect, right? There's still some issues with having only notebooks. There are some pitfalls you need to be aware of. It can be changed too easily. The order execution is not guaranteed, right? If I get a notebook, I cannot really be sure that this cell was running before that cell or after that cell. Maybe someone ran some code and then deleted the cells, and I don't know it. And also, it makes it hard to add unit tests or code reuse or CI. So even though these small imperfections, we still have a huge amount of notebooks, something like 17,000. I checked the names. Only 2,000 of those are called untitled. So the rest are probably really the notebooks that people are using. And we have a lot of weekly users. So how can we make it 100% perfect? How can people feel okay to use their notebook for more use cases? So we try to make some order in the chaos of the notebook, and we tried all of the engineering concepts also onto the notebook platform we have. So we wanted a way for our user, a streamlined, something that will not make them look into the internals of how the notebook works, but still be able to get some, or at least most of the things listed here that are important for a more robust way of working. So for that, we needed a way to run Docker containers in Scala. Now, all the cool people, they do Kubernetes. It's very cool. I think it's hard. We did something harder. We got Docker to run on Hadoop. It's basically available from the latest version, 3.1. They started allowing it, now 3.2. They added some more features to it. It's still clunky. We search on the internet every time we tackle an issue. We don't see anyone, many other companies are doing that, so we're pretty much walking in the dark there, but it's working okay for us now. So basically the way it works, we have an image registry for all of our Docker containers, and we install Docker on all of the nodes of our Hadoop cluster. And then you can actually submit jobs to Hadoop, either with Yarn, which is the resource manager of Hadoop, or with Uzi, which is the scheduler. And then when you submit the job, you specify which image you want to use, and then you can run your Docker container on Hadoop. And that was easy for us because we still believe in data locality, and we invested a lot in Hadoop, and we know how to run the Hadoop. We have a lot of knowledge. So it was easier to us to make Docker work on Hadoop than to go out and learn about Kubernetes and do more things with other clustering technologies. And what we ended up having as images is, first, we created several base images with what we learned from the research environment. We created the base images for our users, usually with PyTorch, TensorFlow, a lot of cool things. But we also gave our users the ability to push images on their own. So some of the projects are just simply building their own Docker file and pushing it, and then they can deploy their application, submit or coordinate their application to run on Hadoop. And the experience that we got as a result of it is a very intuitive thing. Okay, so we developed a small CLI, we call it Captain, and then they can actually take a notebook from the research environment that they developed on the Jupyter environment that we have, and with a single command, they can just submit it and run as a batch job on the cluster. Now, a batch job is already very close to production. They will only have to add a couple of tests, or maybe to go over it and have it code reviewed. But it's got a lot of the robustness of what we search for when we talk about production. And even during the submission itself, we are checking it into Git. We are understanding which image you are using on the research environment, and then we use it the same for you in your batch runs. And it's also just as easy to schedule a job. Okay, so if I'm a data scientist and I have the project I want, I can simply own end-to-end from the research when I created it to the part when I need it to run daily or hourly or any other need that I might have. And that's the basic state of mind that we have when we develop our tools, that we want to keep it as a minimal setup for users. We try to give great defaults, so the way it usually works, that the data scientist starts in the research platform. He has all the dependencies that we got to up to that point, but then he goes on, he builds his own tools, he builds his own solution, and he can bring it back into the research platform. So the back and forth from having something that is on the research side, then moving into production, but then you can reiterate again by putting it back by building a notebook on top of the code that you already have in production. That proved to be a very important thing, because unlike Kaggle or unlike competitions, once you're done with your model, you don't care about it anymore. Here, when we put a model in production, we usually need to debug it like a month later, understand what's happening, or iterate over it, or add a feature to it. So what we enabled throughout, both for the Spark world and for the Python world that we have now, is the ability to start a research, move it to production, but then also the feedback, to do the full loop of getting it back and basing your notebook on the code that you have. And another thing that this whole containerization and approach leads, that advanced users can do what they want. So a user can build his own image, a user can use whatever dependency he wants. Like, we have great setup to get you started, but also unlimited extensibility if you need. And some things that we done, maybe we could have done differently, that we know now that were important, is having all kinds of setup. Like when you invite Python into your organization, there's all kinds of things that you need to be prepared to have in order to make it more effective and easy to use. So one thing that was important was setting up our own PyPy, and the dependency is a bit weird in Python, right? Since we have a lot of JVM people that can use Maven or SBT to package their apps. There was a bit of an issue to do that with Python. We really like Poetry. That's a cool project. I have linked to it here that solves a lot of the dependency management of Python. We use Black for linting. We use Talks for testing. But one of the most important things to do is to build a community in Python. So there's a Slack channel, and more people starting to use Python, or to know that they have the ability to use Python. And then when we have internal talks, people are sharing what stuff they did, what machine learning model they used in TensorFlow or in PyTorch. And then this also gets spread out the word of what tools we have and how can we use Python. And that turned out to be a cool thing. And that's basically it. Any questions?